So what are we doing today? Today we're going to take the methods from a previous lab, the numerical methods, namely Eulers method and improved Eulers method, and then we're going to extend it to the case of a higher order differential equation. We did first order diff EQs before, now we'll extend that to second order. And in some sense, there's just a small intermediate step to get there. If you have a decent grasp of Euler's method, I think this will not be too much of a, of a big leap. If you struggled with Euler's method, hopefully as we go through this, especially to begin with, it'll help solidify what's going on there. But as usual, you're welcome to ask questions and we can, address those as they come up. So let's get into it. With Euler's method on first order differential equations, geometrically what we did was we had a point xy, say some x sub I and then sub y and then a y sub I. And then from there, we approximated a new point using a slope like so. That slope was y prime. And there was a formula for it. There was a formula for it because the differential equation was first order. So we would have something like, for example, y prime plus, let's say, p of xy is equal to some q of x. And then we could rewrite that as y prime is equal to negative p of x. Actually, this is, could it be more general than that? Yeah, I guess it could. I guess it could be even more general. Really what we had was, it's just some function of xy. It could even have things like y double, or like y prime and, or y squared and cosine of y or whatever. Things we wouldn't normally allow for linear. It didn't have to be linear. Just had to be some function of xy that we could write over here. So that allowed us to have a slope that we used to compute the next y value and the next y value in particular. The next x value was going to be easy enough to compute. So we'd say this one is y sub I plus 1. This one is x of I plus 1. Well, I guess this kind of looks like a Q-tip. Interesting. Now, we also needed a step size. That will be similar. So we'd have an h. But that was essentially it. We computed new x values by simply adding h to the last x value, and we sort of just incremented, well, we didn't sort of, we definitely incremented by h each time. So the next x sub I plus 2 would just add another h, and then add another h, and then add another h, and so on. And in order to compute the new y values, we would use h, but we would use h together with the slope. So over here, this change was actually h times the slope, y prime. That gave us the change. To compute the new x values, we just add h. To compute the new y values, we, again, just like with x, we use the old one, we add something. What we add is not just h, but we add h times the slope. All right, well, what changes when we have second order? So now we're going to do Euler's method, but it's going to be second order. And this can be extended to third order and so on. There's not a limit to it. I'm going to forego drawing another picture, but the idea is going to be very similar. What's different here is the following. If we have something like y double prime. Now I'm going to use a specific example. I'm going to use the specific example y double prime plus 3y prime plus 2y is equal to e to the x. What's different here is we don't have a nice formula for, let's say, y prime. We also need to know how to compute, well, let me just leave it at that. We don't have a nice formula for y prime. And in order to address this, what we'll do is we'll actually introduce a new variable. Currently, there are two variables. The variables are x and then y. And then after that, it's just different derivatives of y. But there are just two variables. We're going to introduce a new one. The new variable we'll introduce, let's call it v. So we're going to say v is equal to, we're going to set it equal to y prime. And I see that that purple's a little darker than I like, so let's lighten it up. There we go. Now, if v is equal to y prime, then it follows by taking the derivative on both sides that v prime, and just to make sure you're following me, would you just say in chat, you can private or public, doesn't matter. It's up to you. What is v prime going to be equal to? So v is y prime, then v prime is what? Okay, I see a chunk of responses. See that a lot of people are getting it. If you weren't sure, that's okay. That's kind of why I asked, just to make sure I'm not flying ahead too much. So notice if v is equal to y prime, if we take the derivative of both sides, taking the derivative of v gives us v prime. And if you take the derivative of a derivative, then you get the second derivative. So prime of y prime is y double prime. Now, the reason we do this is so that now we can write this second order differential equation in the following way. We can write it like this. We can say v prime plus 3v, so I'm just writing the v's first, plus 2y is equal to e to the x. So you'll notice I took the y prime here, I replaced it with v prime. I took y double prime and replaced it with v prime. I took y prime and replaced it with v. Otherwise, it's exactly the same. So we took this, replaced it here, we took this, and we replaced it here. Otherwise, it's the same differential equation. Okay, so how is this helpful? Who cares? Why do we bother to do this? Well, you'll notice back up in the first order Eulers method, we had a y double prime is equal to some function of x and y. That allowed us to use this slope to compute a new y value. Now we're in a similar position. Because of how we've set up this differential equation, what we can do is we can say that v prime is now equal to negative 3v plus 2y, or not plus 2y, minus 2y, plus e to the x. Another way of writing this is saying that this is a function of three variables. It's a function of v, of y, and of x, or xyv if you like. Whatever. Order doesn't matter. And now maybe you see some similarity between this, y prime, being a function of x and y, and this, v prime, being a function of v, y, and x. So we have this, and we have this. All right, that's good. Now, the reason we want this is because we will need to find out new v values. And it'll make maybe more sense in a second why I say that, but let me add one more thing to this. Let's see, let's add it right here. And I'm going to put this down here. I'm going to make it a little smaller because I want to highlight these two things. So we have this now system. This is going to be important perhaps a little later when we're actually trying to solve systems. But notice we have a single equation here, and now we have, in some sense, two equations. That's something to keep in mind as we go forward. But let's now actually jump into the calc. And by the calc, I mean, it's called calc for me, but Excel if you're using Microsoft. So let's do that. I'm going to stop share here. And then now I'm going to start sharing LibreOffice Calc. All right. So you should now be able to see what looks like an Excel type sheet. And let me move this out of the way. And okay, that should work. I have a couple different sheets down here. That's from the previous hour, the 9:30 section I have. But I'm going to start a fresh one here. And I'm going to start by calling it the name of the differential equation we'll look at, or just what exactly that differential equation is. So let's look at y double prime plus 3y prime plus 2y is equal to e to the x. That's going to be the differential equation we look at. And we're going to use Eulers' method to start. You may wonder, is there another method? And there is. There's also an improved Eulers method, but if you really got to understand Eulers method to begin with, and once you do, it makes it much easier to try to understand improved Eulers for obvious reasons. So let's start by looking at this differential equation, and I'm going to rewrite it up here just so we can have a visual reminder what we're looking at. Plus 2y is equal to e to the x. Let's also have some starting information or initial value information. Let's say that y of 0 is equal to 1. And let's say that y prime of 0 is equal to 0. Now you can have, well, let me back up. For a second order differential equation, if you want to find, if you either want to do an approximation, numerical methods, or you want to find a solution formula without any parameters, you need two pieces of information because it's second order. For whatever order it is, you need that many pieces of information. Since it's second order, we need two. If it was third order, we'd need 3. If it was fourth order, we would need 4. So we have 2 here. It doesn't have to be y and y prime. This is initial value information. You can also have something called boundary value information, where you'd have y of, let's say, 0, and then y of 5. So you'd have two different starting, what's the right word? Two different values of like y of, or I'm sorry, not, yeah, y of 0 and y of 5. So you wouldn't involve a y prime, just a sort of preview how that can change. But for now, let's color this differential equation. I'm going to color it this sort of light blue. And then I'm going to color these two a magenta. And now I'm going to set this up differently than it is in the write-up. You might like the write-up version better, might work for you. This somehow suits me much more. I think it's more intuitive, but it's totally up to you how you want to do it. We're going to have an X column to hold the X values. Then over here in K, let's actually call this the H column, or hold the H values here. Actually, I'm going to center all of these just because I think that looks nicer, makes it easier to keep track of things. We're going to start with an X value of 0. Why am I starting with 0? I'm starting with 0 because we have y of 0. So the initial x value is 0. Then over here with h, which I'll put in a different color, that won't really matter, but just kind of helps us to keep track of different things. We'll have that h starts out as 0.1. Now, without reference to anything else, we can actually compute all the x values right away. We don't need anything but the step size. What we can do is say that the next x value is going to be equal to, so now I'm going to enter this formula here. We're going to say it's equal to the last one plus, and I'm going to write something, and then I'm going to ask you, is this okay? So let me double check. Okay. Is this going to be an okay formula to write, or is there a problem? So in chat, what do you think? Okay, is it a problem? If you think there is a problem, what is the problem? Okay, good, yeah. So for those of you who gave comments, thank you. They're excellent. I'm not sure what the exact phrasing is in these sheets, but everything you're saying is good. Like we need to lock this value or hold it in place. We do need to add $signs and so on. So however the phrasing should be, we want to make it so that as we copy this formula, we're not changing the cell K3. We always want it to be K3. So yeah, maybe locking is a good way to say that. In order to do that, the syntax is to put $signs around the K. Now, if we, let's say, Control-C, copy, Control-V, paste, we'll notice that as I switch between the two formulas, the C3 and the C4 change, but the K3 remains the same. So that's what we want. So to fix it or to lock it or what have you. Now I am going to copy this formula. I'm going to hold Shift and then the directional arrows and just copy down a bunch. Control-V, paste. You may do the drag. I find that the drag sometimes causes issues, so I like the Control-C, Control-V, but whatever works for you. Now, in theory, what we care about are knowing x, y points. We want to know y values, or we want to know as best we can what the y values are at a given x. So the most important thing after the x values are the y values. We know what y value we have to start with. Since up here we have y of 0 is equal to 1, we can say this is equal to 1. I'll put that in this sort of light magenta color just to highlight that it is an initial value information. And then in order, like let's imagine what we would need to get the next y value. So again, this is going to be something I write that I'll just tell you, it's not going to be correct, but I'm curious if you can see why it's correct. If I did like we had with x, what I would write is the next y value is equal to the previous one and then plus K3. Now I've written that. It's not correct. Why is this not correct? And the reason I'm asking is not to like put everyone on the spot. It's just to see if it's clear or not. Should I explain more? So on. I'm not seeing anything in. Okay, here's some answers are coming in. Okay, so I'm getting a few good answers here and just some good feedback in general, even if you're not sure what it is, even just hearing what you think is useful. It just gives me a sense of where you are. And I'm certainly seeing that it's taking more time to process. So this tells me I should explain a little bit. Let's see. Yeah, I'm actually going to jump out of this back to the iPad screen to really highlight what's going on. I can't show it super well here. So I'm actually going to write what's wrong for now, and we'll fix that formula in a bit. So this formula is not quite correct. So let me change the screen share so I can show you what the difference should be. So I think seeing it makes it a lot easier. We can actually use this diagram for Euler's method. And some students did point out what the issue should be, but it was not as obvious as the other one. So I just want to highlight. if we, let's say, forget about everything but what's going on the x-axis right here, back in just regular Euler's method, in order to get the new x values, we only needed h. So we just add h each time. Just add it over and over and over again. In order to get the new y value, what we want to do is take the previous one and then we add a certain amount to it, which may include, moving it down, but either way. And in order to get that, in order to get this side of this right triangle, notice this triangle has a base of h. It has a hypotenuse that's actually of y prime. Just doing a little bit of geometry, I think Pythagorean theorem would be actually, you just need to know how slope works, rise over run. In order to get this height right here, it has to be h times y prime. And that just comes from the fact that you have this little right triangle here. And in order for all these dimensions to work out, and just how slope is defined as the rise divided by the run, it has to be h times y prime, which you can see, right? If you take rise over the run, you get the slope. The rise, if we didn't know what that was, if we just had rise and we weren't sure what it was, the run is h. I said slop, that should be slope. The slope is going to be this y prime. And we can see just by some simple algebra, I guess you don't even need trig, that this is just y prime times h. So it stems from just a little bit of algebra that you have here with this triangle. Okay, now I will jump back to Excel, or not Excel, to LibreOffice. Okay, here we go. So back in LibreOffice, and just to double check, and if you've written this already, that's okay. Actually, I'm just going to go ahead. I think it's somewhat clear. What we want to do is we want to take this K3, that was the step size, the h, and we want to multiply that by the slope. Now you'll notice here that we're missing a slope. We don't have a slope. So actually, we need some more information. What I'll do right now is I'll just say slope, and I'm going to remove the equal sign so it doesn't yell and say, that doesn't make sense. I'm just going to write what we want to have. It should be D3 plus, the step times the slope, but we're missing the slope. Well, we're missing it being entered, but we do have it. What we want here is the slope y prime. In fact, let me even clarify this more. We want the slope, which is y prime. Now, from there, we actually called it v before when we were looking at it on the iPad screen. So y prime or v, same thing. That's why I have this sort of extra row up here so we can kind of see that it has two different names. This we actually know what it is, what the value is to start with, because we have y prime of 0 is equal to 0 over here. That means that this will be equal to 0. And I'll color that magenta because it is starting value or initial value information. Now we can actually finish this formula because we do have v, which is the slope, y prime. So what we do is we back over here, I'll now hit enter so the calc knows that I'm trying to do like enter a formula. And now for the slope y prime, that's going to be exactly this cell up here, which is E3. And if we hit enter, the y value shouldn't change because the slope was 0. So that makes sense. But as v slash y prime changes, then we will have changes in y. Okay. Now, to hopefully reinforce this point, if I want to find out what this y value should be in D5, what we would need is, again, a slope, a new v. Before, with Euler's method and first-order differential equations, we had a formula for what V should be. So we could just say that no matter what X and Y are, we know what V should be. We do not have a formula now. So we can't just enter a formula into this column E. There is none. We had an initial value of 0, but we don't have a formula to compute the next V. So we have to compute V somehow. All right. And now if you are making this connection, or you kind of see where this is going, that's great. I'm trying to lead you there, so it really makes it much easier for you later. But if we take this and we want to say, well, what should the new V value be? Kind of like we've done previously, whenever we've computed a new value, we tended to take the old one. In this case, I'll take E3, the last V value, which was 0. And then we add to it the step size, which is fixed K3. And now we should multiply it by something. In private chat, whether you know or not, you just private chat me. I want to hear what you think. I don't care if it's right or wrong. I just want to know. What do you think we should multiply by here? It should be the step times what? So we got times, but we're leaving it hanging. And there's a few potential names for this thing, but as long as you know what the thing should be, that's all that matters. So what do you think we should multiply? We took the last one, we added the step size, and it's going to be very similar to what we did for Y. So what are your thoughts? Okay, I'm seeing some good comments so far. All right. Yeah. So for those of you who put something in private chat, I appreciate it. It gives me a window into what you're thinking, which helps me direct the instruction. So thank you. Just like in the case where we had Y and we're trying to compute a new Y, let's go back and look at the formula. So I'll erase this for a second so it doesn't holler. Notice what we did is we took the old one, the D3 cell, we added the step, which is fixed K3, and then we multiplied by the slope of Y. It's going to be no different here. We're going to take the last V value. We're going to add to it the step, K3, times the slope. And now the slope, again, we're missing. So we need a V prime. So I'll say slope V prime. I'll get rid of the equal just so it doesn't think we're trying to compute something and then get confused. So indeed, what we want here is a V prime. Just like here, and actually maybe I'll put it up there, kind of keep it consistent. All right, so now what is V prime? We don't have an initial V prime listed, but we can compute it pretty easily. That V prime, which is Y double prime. So if you said Y double prime, it's the same thing. You got the right idea. So now what we're going to do is we're going to say V prime is equal to, and just like we looked at it in the with the iPad, we're going to take negative 3V minus 2y plus e to the x. That's making the substitution that V is Y prime, Y double prime is V prime, and so on, and just isolating V prime. So it's taking this and doing some substitutions and rearranging. In fact, this whole column is going to stem exactly from this here. Now, in order to compute this, the first V prime, we do have a formula. So what we can do is we can say this is equal to, it's going to be negative 3 times V. V is the E column for me. It may be different for you. But then that's going to be negative 2 times Y. Y for me is the D column. And then plus exp for e to the, and then it's e to the x. So I'll say exp, and then for me, it'll be the C column, and that'll give me C3. I hit enter, and there we go. There's the V prime. Now we have what we need in order to compute the new V. Remember here we were missing the slope V prime, so we couldn't quite complete it, but now we can. So with V, we can say this is equal to the last V, which is E3, plus the step, which is fixed K3, times the slope V prime, and that's simply going to be, for me at least, the cell F3. So I'll hit equal or hit enter, and there we go. And now we have everything we need. In fact, we can even just take this F3 cell and we can copy paste it like there. And someone asked a question, what was the exponent value? The exponent value here was, since we wanted e to the x, the syntax for that was exp of, and then in place we would have quote unquote the x, but the x for me at least is going to be the cell C3. So it's exp of C3. If that answers your question, but if it doesn't answer, let me know and I'll try to rephrase it or address it better. Okay, cool. All right, I am going to change this. This is not necessary, but I just like to, maybe you've noticed I like things to be kind of neat and orderly when I can. So I'm going to change it to just 5 decimal places so it's nice and even as we add more. At this point, we have everything we need to just reiterate this over and over. So I'm going to copy D4, E4, F4, those cells for me. You may have different ones. And then I'm going to hold shift as I move the directional arrows, and then I'm going to move this down, and I'm going to Control V, paste it. And while I'm at it, I'm going to change the formatting so that all of the columns here have just 5 decimal places. There's no particular reason I chose 5. It just seemed like enough to be meaningful, but not so much that it got too cluttered. And I'll narrow these columns a bit. And there we go. On top of Y here, I'm going to put the label approximate Y. I'm going to put that in a stark black fill to really highlight. Just to remind us that we're approximating these Y values here in this column D. And I'm going to check. Can you show the formula for V one more time? Yeah, actually, I'm going to highlight the cells for, actually, let me annotate. Do note this. I think if what I'm about to show makes sense, I think it will be helpful. Here's the, actually, I don't like that orange. Let's do blue. So notice this formula box, and then notice when I look between these two. Like, how do I get Y? How do I get V? Let's notice, or let's kind of look at the similarities and differences. So notice as I'm just going to switch back and forth between D4 and E4. Notice these formulas are identical with the exception that there's just a shifting in columns. And this is why I like to set up this sheet this way, or do Euler's method this way, is it's, for me, really easy to see how we come up with the new Y and the new V. The new Y comes about as taking D3, the last Y value, and adding the slope, the step times the slope. And then with the other one, notice is exactly the same. All we're doing is we're changing D3 and E3 to E3 and F3. So it's just a matter of moving the columns over, if you will, or moving over which columns you're picking from. But otherwise, the formula is exactly the same structure. So to the person who asked, showing the formula for V one more time, there it is, and then hopefully it makes maybe a little more sense why it is that way, or how it relates to what else we did. And then someone else asked, how did you fix the decimal places? We did that by, let me clear the annotation. We did that by, you can select as many cells as you want. Maybe I'll select a whole column, or you could do 3 columns at once if you like, just by holding Shift and clicking. Right click on the columns, or I think actually anywhere would work. Yeah, anywhere in the selected area. Click Format Cells. Go to Numbers, the first tab. There are lots of tabs, but you want to go to Numbers. And then while on Number in Category, I change the decimal places here to 5. And that's how you do that. So right click, Format Cells, go to Numbers tab, and adjust decimal places. Alrighty. Now I was talking here about an approximate Y, and the reason is because we'll want to look at an exact Y and see what the difference is between the approximated one and the exact. Now, if you were actually using numerical methods in, as a scientist or as an engineer to how, like if you started with a model, a differential equation that modeled some physical behavior, there was not a nice solution formula, because if there was, and you could get it easily, you would just use that and you would never think about numerical methods. But oftentimes you can't. So numerical methods is all you have. So we're lucky to even have it sometimes, or to even have it as an option. If you were using the numerical methods, you would almost assuredly not have a nice solution formula, or it would be too hard to compute. So numerical methods would somehow be much easier. And when you're computing these values, you're getting approximations. These are not exact values. So it's nice to know how far from the actual you are. And doing error approximation is a big thing of itself, like really understanding how far you are away from the actual like perfect solution. But in this case, we're working with differential equations where we can compute a solution formula, and then we can see exactly what the difference is between our approximation and our exact solution. So this is not always possible, except we're working with differential equations that are easy enough that we can find such a solution relatively easily. So we will want to compare the two. Now, before that, I actually want to do something else real quick. I'm going to add a new sheet, put it next to the current one. I'm going to select the columns A through K. If I selected everything with Control A, it usually doesn't work for me that way. I'm going to then highlight the same columns. I'm going to paste. So I Control C back here, Control V back here. Now we have a new sheet. And I'm going to change the differential equation slightly. I'm going to change it to be the homogeneous version of the one we were just looking at. Now you may ask, why am I doing this? I'm doing this because we have in the lab write-up a exact solution formula for the homogeneous one. So if we change this e to x to 0, and then over here I change this e to the x to 0, and then I change each of these formulas. So notice every place I had the exponential before, I'm going to get rid of that because I changed the differential equation. And I'm going to copy, paste this down. Okay, there we go, which changes everything else automatically, which is nice. All right, so just to note, what did I just do? I created a new sheet. On that new sheet, it's a different differential equation. I'm switching back and forth between the sheets, alternating. And notice here's a good place for annotation. Notice that there is a change, and that change is exactly here, it's over here, and it will be in this formula box here when I select. So notice so notice the change between these. The e to the x becomes 0, which means it disappears, and it drops off in the formula box. Okay, so I'm alternating between these two to really highlight, and now I want to stop doing that, so I will. The reason I did this was to show you that you can make slight changes to this setup. For example, if you encounter new differential equations, all that really changes, like new second order ones, is the formula here up in this box that's in the V column. Everything else is going to work out the same no matter what. Like the formulas are not going to change between the sheets. So if you have a good setup now, you can just do, like, you can duplicate the sheet or copy paste the columns and make slight changes to the formulas, and everything else will be like, if you've done any coding, you know what this is all about. You take a lot of times existing code and you modify it for your own purposes. So it's the same thing here. We've essentially set up the code that we need, and it is code in a way. And we just made a little change here. Now, the reason I switched to this particular change is because now we can do an exact y. So I'll put that again in the black to match up with the approximate y. And now here, that is going to be, so now I'm pulling from the lab here, from the lab write-up. The exact formula is going to be 2e to the negative x, minus e to the negative 2x. Negative 2x. Okay. That's the exact. Now, if we enter that as a formula, I'm going to get rid of the annotation. If we enter that as a formula, what we get is it's equal to 2 times exponential negative x, which for me is the C3 cell, minus exponential negative 2 times, again, the C3 cell. So what's that formula? It's just the exact formula above, but in the calc version of it. And when I say calc, I mean LibreOffice calc version or Excel version. And now we can copy all these down. I'm going to again change the column to only have 5 decimal places. 1, 2, 3, 4, 5. And now we can see somewhat the difference between the two. Like we can kind of compare these. A nice way to compare them is using relative error. So for the relative error, to compute that, we take exact y minus approximate y, and then we divide that whole thing by exact y. And I am going to, oops, put that, I'd like to show that so everyone can read it nicely. Actually, let's try this. There we go. That's good. Exact y minus approximate y, divide that whole thing by the exact y. So that's what we're gonna write here. So we're gonna say this is equal to the exact y minus the approximate y divided by the exact y. It should be 0 to start with because we have an exact point. And then I'm going to change this to a percentage with 2 decimal places, and then take and copy this down. And if you're not sure what I'm doing here, it's no different than what we did in the first Eulers method, first numerical approximations lab. We're just computing the relative error here. Okay, this really sets up everything for regular Eulers method. Just like in the previous lab, there is a previous numerical methods lab, there is an improved Eulers method, but I wanted to make sure to try to really make it clear what's going on in the regular Eulers method. Hopefully that's the case. If you are still confused about the improved Eulers method after looking this over, there's time tomorrow where I'll be in office hours. You're welcome to stop by. I'm also in a help session. You're welcome to stop by. We can look at it. You can also ask a question in your kind of weekly questions thing that I grade and just say, yeah, I'm really confused. Can we go over it in recitation? And we can do that as well. But for now, you all have a good day and we'll talk to you later. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.